Okay, so we're looking at a diverging lens, and now we want to look at how it produces an image. So drawing out the same exact lens, it's going to have the same focal length, so it's the same characteristic. And this time what we're going to do is put an object out, just like we did with the case earlier with the convex lens. And so in this case, I'm going to put it about, we'll put it 7 centimeters out from the lens. Put it right here. And I'm going to make its height the same as we did before. I'm going to make its height 2 centimeters. I'm trying to be fairly exact, but I'm not going to stress too much about that, because we can always do the calculation, but we're going to give it some effort. Okay, so we've got this terrible looking tree that's going to be our object. I'm just going to note that it's got a height of 2 centimeters. Okay, and I already know I'm going to have a focal point here. We map that out, and of course we also know that there's going to be one on the other side as well. I'm just going to make a note of where that's going to be. 3 centimeters out, we've got a focal point here. Okay. And again, for the same reason as we did this for the convex case, you could have rays coming in as we did up here, and we're going to see this convergence here when we trace those rays back. And we could do it from the other side as well, and we chart out the focal point from that direction. Okay, so we've got this object out here at about 7 centimeters away. So I'm just going to make a little note of that down at the bottom. Okay, so our S, which is our distance to the object, is 7.0 centimeters. And we already know this focal length. Okay, so let's do some tracing. We've got the easiest thing to do to start out with is to do one of the rays we've already done up here, which is we get a ray that's going parallel to the axis. Be a little careful. Okay. So we're going to have this ray that goes straight from the top, parallel to the axis, and we know exactly what it's going to do. We've already done that. So it's going to move and diverge sharply away, like that, and we're able to trace this back through the focal point here. So that's our first helpful ray to look at how this is behaving. The next one, as before, is going to be, we can send a ray straight through the center of the lens, and if we do that, it's not going to change its direction. Okay, so I've got a little arrow on it, a little arrow on it here. Okay, and the next one that we can draw is we want to draw another ray such that on the other side here it's going to be parallel to the axis. And the way that we do that is again thinking about, okay, so we're thinking about this in both directions. So it's going to be aligned such that it would pass through the focal point, but it's going to in fact refract such that it is parallel to that axis. Okay. So in this case, we can then trace this back. In dotted lines, and we see that these are all converging here. So we've got this point of convergence between this ray and the lines that we've traced back from the other rays. And this is going to be where we produce our image. We're going to have this little tree here. So we can already say a few things about the image that's produced here. One, it is smaller than the original object. 2, it's right side up. And 3, we can get a sense of where that distance is from the lens. And we're looking like we've got a distance that is just over 2 centimeters. It's about 2.1 centimeters here. So I'm going to just make a note of that at the bottom. So we're going to go just past the 2 centimeter mark. We've got a S primed, 2.1 centimeters. Okay. So we've done this all by ray tracing, but of course we can do this in a more mathematical sense and do this with equations. And we'll see how close we got with our diagrams. Okay. Oh, I didn't get the height. Yeah, so I'll try and get the height here as well. So we're looking like just over about 0.6 of a centimeter. So we got an H primed of approximately 0.6 centimeters. Okay, so how we do this in terms of a calculation is going to be the same way as we did before. We're going to start with our thin lens equation. So 1 over S plus 1 over S primed is equal to 1 over F. Our distances to the original object, the image, and the focal length. Okay, so we can also rearrange this and solve for our S prime, which is the first thing we want. And that'll be our S times F over S minus F. Okay, so here we're going to have S, well that in this case is going to be 7 centimeters. And then we have our focal length. And this is going to be slightly different for the diverging lens. So in this case, F is written is kind of negative for the diverging lens case. Okay, so that's important. And then we get S, again, 7 centimeters minus, this is going to be minus, so it's plus 3 centimeters. And we get S primed value of minus 21 centimeters squared over 10 centimeters. So we get an S prime value of minus 2.1 centimeters. Okay, and in this case, we have this negative again, and that means image is on the same side as the object. And we saw that before in the case of the convex lens producing an image when the object was inside the focal point. Okay, now the only thing left here, well, we can compare. We actually did a really good job here getting a diagram distance to the image. It came out exactly to the calculation. Okay, so one last thing we could do, we could look at the magnification. So I'll draw this up here and say, well, our magnification is minus S primed over S. And that's going to be, I've got 2.1, this was the same. Over our original distance away. That was 2. No, that was 7. 7 centimeters, sorry. And so we've got a magnification of essentially 0.3. We've got a magnification factor of 0.3, and that aligns here, right? We're getting a much smaller image, about just about a third. And if we want to know what our resulting height of the image is, it's again going to be this absolute value of the magnification. The magnification being positive told us it was in the orientation that the original object is in. And so it's going to be 0.3 times the height. The original height was 2 centimeters. And so we get a height that's 0.6 centimeters. Okay, so surprisingly, I tried pretty hard to get the diagram fairly well, and we see the same result here. So we can do it very carefully by drawing it all out, but of course it's actually much faster to do the equation and do the calculation. But you get the same answer either way, and that's always nice.